Hello everyone, welcome back to the channel. So today we are doing Leetcode 743 network delay. Let's have a look at what the problem statement says. It says you're given a network of n nodes, something like this. Now you're also given times, which is a 2D vector, and wherein every vector is source, destination, and how much time, or you can say how much cost it takes you to go from the source to destination. All right, now what they're doing is they are transmitting a signal from a given node k, and what we need to do is we need to return the minimum time that it takes for all the n nodes to receive that signal. If it's impossible, we return -1. Now for example, in this particular scenario, 2 is the starting node, and we can very clearly see that after 1 second, node 1 and node 3 will receive the signal, and after one further second, 4 is also going to receive the signal. So it takes a time of 2 seconds in order for all the nodes to receive the signal. Over here we have two nodes 1 and 2, and there is an outgoing edge from 1 to 2 with a weight of 1. Now they're saying that 1 is the starting point. All right, so obviously it takes one unit of time, it takes 1 second for all the nodes to receive the signal. Now, keeping the input the same, but if we just change the starting point, if we take 2 as the starting point, now there is no way that all the nodes can receive the signal, because there is no outgoing edge from 2 to 1. So in this scenario, our output is going to be -1. So if all the nodes, or if even any one node is unreachable, what we are going to do is we are going to return -1. Right. So having said that, let's have a look at a bit more complex scenario. Let's say that this is the network, this is the connected weighted graph that we are given. All right, so the graph is weighted. This is the weighted graph that we are given, and what I have done is I have already gone on to represent that particular graph in the form of an adjacency list. Now what we need, let me write that down over here, is the minimum time for reaching all nodes, you can say minimum time to reach all nodes, for the signal to reach all nodes, isn't it? So what can I do in this scenario? Can I do a simple sort of DFS or BFS? Would that solve my problem? Let's see. So I have the adjacency list, and let's say that I do DFS first, let's say. So from 1, let me change the color over here. Let's say I choose the red color. So I'm initially at the starting point, and obviously the in order to go from the starting point to the starting point itself, it takes you no amount of time. So let me update this as 0. From 1 you're going to reach 2. All right, you're going to reach 2, and in order to go from 1 to 2, it takes you 10 units of time, and 10 is shorter than infinite. So what you're going to do is you're going to update over here, you're going to make it 10. What is this? This is simply a vector, you can say, as minimum time, and what it does is it tracks the minimum time to reach all nodes. All right, to reach all nodes. Perfect. All right. Now, since you are at 2, you were initially at 1, now you are at 2, and from 2 you can only go to 3. So what you're going to do is you're going to reach 3, and in order to reach 3, what you need is 10, but 10 plus this particular 10 as well, isn't it? So in order to update this particular cost, you need two things. Number one, the current cost, which in this scenario is 10. So in order to reach 2, you need 10 cost, plus the, you can say, upcoming cost. All right, the upcoming cost, which is also in this scenario 10. So 10 plus 10 gives you 20. Perfect. So let me do 20 over here. Now once you have reached 3, you can only go to 4. So what you're going to do is you're going to reach 4. The current cost is 20. It takes a further 10 units to reach 4. So it's going to become 30. And then from 4, you can reach 5 with a further 10 units cost. So it's going to become 40. Now, once you reach 5, there is nowhere else you can go. So you're going to go back to to 4. Similarly, from 4 you're going to go back to 3. Then from 3 you're going to go back to 2, right? From 2 you can also go nowhere, and then from 2 ultimately you're going to go back till 1. Now in 1 we only processed this particular node, so we have only till now we have only processed this particular path, isn't it? We have only processed this particular path, but this particular option is still not discovered, right? So what I will do is now I will discover this particular option. So it says that in order to go from 1 to 3, and in order to reach 1 you need no cost at all. You're going 1 to 3 and it's taking you 17 cost. Is 17 less than 20? Yes, it is. So what you're going to do is you're going to erase this 20 and make it 17, right? Similarly, you can go to 4 using a cost of 15. So is 15 greater or is 30? 30 is greater. So why not reach, since we are trying to minimize the time, why not reach 15 via this path? Via this path directly. Why go all the way around? Are you getting my point? And similarly, you can go to 5. You can go to 5 using this 30. Using this 30. Right? So why not go to 5 directly? Now that I observe, I actually made a small mistake. I think or is it correct? Because if you think about it, I can go to 4 and then 5, isn't it? So that's going to update my cost as well, isn't it? I can directly go to 4 from 1, which makes it 15, and then I can go from 4 to 5, which makes it even shorter than 30, which gives me a time of 25. So rather than just going and stopping at that point, let me make this correction. The time was what? 10, 20, 30, and 40, right? So when you reach 17 from 3, the first thing that you do is you update this. But then you don't just stop at that point. You don't just stop, right? Right now, right now, let me, yeah. Right now you're standing at 3. So what you're going to do is you're going to go to 4. You're going to go to 4. Now it takes you 17 units of time to reach 3. It's going to take you 27 units of time to reach 4. So 27 units of time to reach 4, and then 37 units of time to reach 5, isn't it? So that is how the DFS works. So from 1 you go to 3, from 3 you go to 4, from 4 basically you go to 5, and then you backtrack, isn't it? So yeah, this is also done. Now if I, for example, directly go to 4, it takes me 15. So what I'm doing is I'm going directly to 4. 15 is obviously much shorter than 27, so I'm going to update this, and then from 4 I can go to 5 with 10 cost. So this is going to become what? 25. Perfect. Now let's say that I change this to maybe 23. All right, let's say I change this to 23. So now rather than going from 5 to 30, I'm saying that you can go from 1 to 5 using a cost of, let's say, 23. Okay. So now when I stumble upon this edge, I compare 23 with 25 and I see that, okay, 23 is my answer. Now, what you have right now inside the minimum time vector is the minimum time to reach all the nodes. So you are 100% guaranteed that after 23 seconds have passed, all the nodes must have received the signal. That's it. There is nothing more to this particular question, right? And you could very well do this with BFS as well. I have done this using DFS, but you can very clearly do this using a DFS approach as well. So let's see how we can convert whatever we have discussed into our code. First of all, what I will do is I will create an unordered map of type int comma pair of int. Now why am I taking pair of int comma int? The reason is, let me open this up at this side. The reason is because in the adjacency list I need to store two things. Number one thing is the destination basically, and the other thing is the weight as well. So that is why I have taken pair of int comma int over here. Then what I'm going to do is I'm going to say for vector int edge inside of times, I know for a fact that edge has basically three things, right? Edge, you can see, has three things, 2 comma 1 comma 1. So it has first of all the source, so that is going to be edge of 0. Then I have, let me copy and paste this a couple of times, then I have v, which is basically the destination, and then I have the cost, so the time that it takes to reach a certain a certain place. What I'm going to do is inside of my map, in the mp of u, mp of u basically is an array. It should be an array. Actually, I have made a mistake over here. It shouldn't be pair of end comment. It can be like there are multiple outgoing edges from a certain node, right? So this is not pair of end comment. It's a vector of pair of end comment. So right now over here I need to make this change. I need to say that against a single integer you can have a vector of pair. All right. And so mp of u is basically a vector, and what I'm going to do inside of it is I'm going to push back a pair which is v comma cost, so destination comma cost. This is going to make the adjacency list for me. And then what I need to do is, let's see, then what I need to do, what I need to do is I need to do the bfs or the dfs, like we said. So let's say that I call a DFS function and I pass inside of it what? I need to create a vector int minimum time. The size of it is going to be, let me, if we have n nodes, n is given to us, right? That's a good thing, n is given to us. What I'm going to do is, since they have started indexing from 1, what I'm going to do is I'm going to create n plus 1 vector, so that I can reach up to n. And 0 is, if it's 0, the index 0 is not going to be used at all. And what I'm going to do is I'm going to fill all the values initially with integer max. So just like we had infinity over here, this int max actually works as infinity. So I have the minimum time vector. Perfect. I have the adjacency list. And dfs, I need to start from what? I need to start from k, because k is actually my starting point. I need to pass the minimum time inside of here, and I need to pass the adjacency list over here as well. Perfect. Perfect. Now I need to create the dfs function. Let's say k is basically my current node. Then I have vector of int minimum time. Let me write that down, copy that down, and it's going to be passed by reference. Why I'm passing it by reference is because I need the values to be saved. I need the values to be saved, right? And similarly, what I'm going to do is I'm going to pass this unordered map as well, and I'm going to pass it by reference. Why? Because it's going to prove, you can say, it's going to prove beneficial in terms of the time complexity, because every time it's not going to make a new copy of the map. It's just going to reuse the copy that we have. So that's actually an advantage of passing by reference, right? Let me, yeah, enlarge this a bit. Now what I need to do is, right now I'm standing at 1, right? Right now, as you know, I'm standing at 1. Let me erase this. Let me write them down again. So 1, 2, 3, 4, and 5. Right now I'm standing at 1. What I will do is I will go to 2, right? I will go to 2. Now there is one thing that actually I need to take care of, and that thing is whether or not I can have cycles inside of my graph. So all the pairs are unique. There are no multiple edges, and there is there isn't written that there cannot be a cycle. But then if there is a cycle, I'll be stuck in an infinite loop, right? And for that I will need sort of some sort of like a visited array or something, since like if you have visited something in this particular cycle, you don't need to visit it again. So right now I'm not taking any visited array, but if the inputs have the situation wherein you could have a cycle, then we'll modify it at that time. All right, perfect. So we are assuming that there is a cycle can't, the inputs are free of any cycle. What I'm going to do is I'm first of all going to see where I can go from my current node. there can be multiple places from where I can go from my current node, right? So look where you can go from current node. And how can I see that? I'm just going to see for using a for loop for int neighbor ngbr inside of mp of current. So where can I go basically from my current node? Where can I go? And I'm going to visit them one by one. So what I'm going to do is I'm going to visit that particular node, right? I'm going to visit that particular node, but before that, actually, let me make this change. MP of k needs to be 0 because I'm going from k, right? This is something that I did in the initialization step. MP of k equals 0. And now I need to see where I can go from k. I can go to multiple places. What I will do is I'll just visit those places. So I will call the DFS function, and let's say I need to pass another variable over here, which is going to be 0, which is the current cost that I have, right? The current cost. So you see, we have two things, current cost and upcoming cost. So this particular variable, it takes care of what the current cost is. What I will do is I will call DFS onto the neighbor, and I will add what? So you see, MP of current is actually not going to be an integer, it's going to be a pair of integer, pair of int comma int, right? And this pair is going to have two things. It's going to have the actual neighbor. Let me say that this is PR. The actual neighbor int ngbr is going to be pair dot first, and int cost is it's actually going to be, or not cost, you can say value is going to be, or you know what, let me give them even more meaningful name, upcoming cost, and this is my current cost. Okay, perfect. Upcoming cost is going to be pr dot second. Perfect, this works. All right, so it's going to be current cost plus upcoming cost, and then I need to pass the minimum time as is and the mp as is as well. Perfect. So, and rather than doing mp of k equals 0 over here, since I'm passing the cost as 0, I can do that over here, right? It's going to update for each and every node. So as soon as you enter inside the DFS function, what you need to do is inside minimum time, you need to do what the current value of minimum time already is. So I can say minimum time of current, whatever the current values, it can be that the path which you are taking right now has a greater cost than what was already discovered, right? So minimum of what it already is and what the new thing is. The new thing is basically current cost, right? Perfect. So in the first step, what it's going to do is it's going to compare infinity with 0, and it's going to mark the starting point, the starting node. It's going to assign the starting node a weight of 0. Perfect. And then for each and every upcoming call, what it's going to do is it's going to add the upcoming cost to current cost, and that particular thing is going to become the current cost. You're going to assign it to minimum time of current. So that is going to take care of all the cycle. Perfect. Okay, what else do I need to do? I think this is enough. This seems to me as enough. And one thing which maybe I can do is keep track of what the maximum values, but that I can do inside of one for loop over here. So for int I equals 1, I is less than equal to n, I plus plus. What I'm going to do is I'm going to take an answer as integer max, and I'm going to say ans is equals to minimum of ans comma min time of I, right? I'm going to ultimately return whatever the answer is. Let's see if it passes the example test cases. Why minimum current? Where did I make that? Minimum time. Minimum time. Wrong answer. Why is it giving me a wrong answer? It says 0. Oh, okay. No. Actually, I need to maximize this. I need to take the maximum amongst all the values. So you see 0, 10, 17, 15, 23. The maximum time which is there is 23, so that's going to be my answer. Oh, it's giving me int max. Why is it giving me int max? It shouldn't. Why is it giving me int max? So if it's int max, actually that means that the node is unreachable, right? The node is unreachable. Else answer. But then it shouldn't be like that. Why is it? Because I passed the neighbor becomes the current, post gets updated, minimum time remains as is, and then MP. Why is it not giving me the right answer? Let's think about it. It's 3 is passed because it's unreachable, but then I shouldn't have an int max in both of these scenarios. I should have different value. So you say minimum time of current is minimum of minimum time current cost. You have a vector integer of minimum time and then MP. Okay, so you can go to if we take a look at this particular test case, this is actually the one which is failing, right? So if I enlarge this a bit, why is this failing? So inside of my adjacency list, I will have v comma cost. So from 2 I can go to 1, from 2 I can go to 3, and then from 3 I can go to 4. So mp of u dot pushback b comma cost. This is perfect, I think, right? Because the test case is something like this: 2 to 1 1, 2 to 3 1, and then 3 to 4 1. U, v, and cost. Why is it not working? I've started from 1. Oh, sorry, I need to take this as int min, because I'm maximizing, right? But there is nothing which is greater than int min, so that is why actually a very silly mistake. The example test cases get passed. Let's see if it passes all the other test cases as well. It gives us a runtime error. Why does it give us a runtime error? Because I think we have a cycle, the Stack Overflow. So you go from 1 to 2 and then you go from 2 to 1 back. So there can be a scenario where you have a cycle and you will need to manage that inside of the code. So you see the test case that we had that was failing was something like this. So it you have two nodes, 1 and 2. So we can take arbitrary values. Let's say something like this. So I'm going to get stuck. I go from 1 to 2, then I go from 2 to 1, so on and so forth, so on and so forth. So in order to avoid that, what I need to do is I need to take a visited would I need a visited array, or can I work without it as well? So I can say um how can I detect that I have already visited that node? I think the simplest way to do that will be by taking a vector of int visited. That will be n plus 1. Everyone is going to be false initially, and I need to pass that inside of my code, inside of this particular line. Sorry, visited, right? I pass that over here, and over here what I'm going to do is just copy and paste this, and rather than this is going to be a boolean, this is going to be visited. And what I will do is something like this. So you see, when I enter inside a DFS call, I'm going to mark that particular node as true. And when I'm leaving that particular node, after all the DFS is done, after all the work is done, I'm going to mark it as false. Why it's important to mark it as false is because you see, just like in this particular scenario, we were visiting for multiple times. So first from this particular route, then from 134, and then from 1 to 4 directly, right? So we had multiple paths in order to visit 4. But then, so it's important for you to visit it's important for you to make sure that you can visit a node in another cycle. it shouldn't be visited in the same cycle. So for example, if you're going from 1 to 2 to 3 to 4, you cannot go from 4 to 1, because you have 1 already present in the current cycle, right? I hope that makes sense. So what I'm going to do is, over here I'm going to check if visited of ngbr, if visited of ngbr equals to false, only then make the recursive calls, else you don't need to make any recursive call. All right, perfect. Compilation error, why? Oh sorry, I forgot to pass minimum time and then visited over here. Hope this passes all the example test cases. Vector of boolean cannot, what is happening? uh Minimum time and then visited, right? It's the fourth thing that we have, where line number 33. Okay, k0 minimum time and visited, vector of boolean, sorry, vector of boolean. All right, this passes all the example test cases. Let's see if it passes all the other ones as well. And it gives us a time limit exceeded error. So it tells us that you need something which is much more efficient than this. So you can't just go around bfs, or doing bfs. You need something which is more optimal. And let's take a look at what the constraints are. So your k can be anything. K is your starting point. Times dot length can be 6000. So at maximum you can have 6000 edges. At maximum you can have 6000 edges. And weight can be anything. All right, sure, at maximum you can have 6000 edges. And what we're doing is, right now what we are doing is, we are trying to explore all the possible paths. So we can very clearly see that trying to go on all the possible paths is not working for us. So uh, what can be an optimal approach? What can be better than this? Now, one optimization that is coming into my mind is that what we need to basically do is, we need to make sure that when we reach a node, we reach it using the minimum time possible, using the minimum cost possible, right? So why are we not thinking in terms of the Dijkstra's algorithm? Dijkstra's algorithm makes sure that when you are reaching a node, you are reaching it using the minimum possible cost, right? And we know for a fact that Dijkstra's algorithm uses the priority queue technique. So let's see how we can work using Dijkstra's algorithm. Let me make some changes. Okay, so here I have made a priority queue, and what we are going to do is, we're going to start from our starting point. All right. So initially, what I'll do is, I'll push inside the priority queue a pair, which is 0 comma start, whatever start is. In this case, it's 1. All right. So I'll pop this. The very first thing that I pop is going to be the 0 comma 1, and let me create two variables over here. The first variable is going to be the current node. All right, that is 1, and the current cost. So let's say current cost, that is 0 right now. I pop this and I see, okay, now I'm over here. Where can I go from 1? I can go to multiple places, 2, 3, 17, 15, and 13. Meanwhile, I'll have the same minimum time logic over here. Initially, this is 0 and all of these are infinity. Okay, so only the starting point is 0 and the rest of them are infinity. So I see that, okay, from 1 I can go to 2 using a cost of 10. Is that less than what the current time is at 2? That is, so I update this and then I push it into the priority queue, because this is an optimal path. This is a better path that I can explore. So I will push 2 comma 10 inside of here. All right, sure. Similarly, where else I can go from 1, I can go to 3 using 17, and 17 is better. So I will write 17 over here and I'll push 3 comma 17 over here. 3 comma 17 actually is going to be beneath 2 comma 10. Why? Because this is going to be obviously a minimum heap. So 3 comma 17 is going to be over here, and obviously minimum heap. Why? Because we are trying to minimize minimize the time to reach all the nodes, right? So the next time that I pop a node from the priority queue, it should be the one which gives me the overall lesser cost, right? Makes sense. So yeah, over here I can go visit for using a cost of 15. So I'm going to make that change, and it's going to be in between both of these nodes. So let me make some space over here. 4 comma 15, perfect. And then I can visit 5 using a cost of 13. So 13, and it's going to be between 2 comma 10, and so I can visit 5 using a cost of 13. Now this makes a lot of sense, right? Perfect. I have visited one. Now what I will do is I will pop this particular uh, pair from the priority queue, and my current node is going to be 2, and the current cost is going to be how much? The current cost is going to be I think it's going to be 10. Yeah, makes sense. I remove it from the priority queue. I remove it from the priority queue, and then I see basically where can I go from, where I can go from 2. So from 2 I can only go to 3 using a cost of 10, right? So the new cost, basically this thing, the new cost, again it's going to be the same formula. The new cost is going to be made up of two things: the current cost plus the upcoming cost. All right, so the current cost is 10, the upcoming cost is 10. It makes the new cost up to be 20, and you can very easily see that 20 is not less than 17. So I will not update it, neither will I push the pair inside the queue. Why? Because I already have a better way to reach 3. Makes sense. I already have a better way to reach 3. All right, perfect. So yeah, I can go nowhere else from 2, so that's it. Then I remove this particular node from my this particular pair from my priority queue, 5 comma 13. The current node is 5, the current cost is 13. All right, I remove this, and I observe where can I go from node 5. I can go exactly nowhere, right? So that's it for 5. Then I remove 4 comma 15. 4 comma 15, I see where I can go from 4. I can go from 4 to 5 using a cost of 10, but then 15 plus 10 makes 25. Why would I update an already shorter cost, right? So I won't update it, and neither will I push it into the pair into the priority queue. Similarly, at last I pop this. The current node is 3. The current cost is 17, and I have already visited uh, 3 using a cost of 17, right? I have already done so. So mm, I don't need to update it, and nothing happens. So yeah, that's it. So you see, rather than hitting multiple DFS and rather than traversing all those paths, I got the minimum time array. I got the minimum time array in just a single, you can say, uh, a single traversal. Now, why does Dijkstra fit this particular problem? Because it tells you the minimum time to reach all nodes from a single source, and that single source in this scenario is what? It's nothing other than the starting node. All right, so that is why Dijkstra's algorithm perfectly fits our use case over here. So now let's have a look at how we can convert this into our code. So what I'll do is I'll just simply remove the DFS function, right? I'll just simply remove the DFS function, and over here as well, I don't need the visited anymore. And I'll just rather than doing DFS, I am going to apply the Dijkstra's algorithm. Dijkstra's algorithm. So first of all, in order for Dijkstra's algorithm implementation, I need a priority queue. I need a priority queue of type what? Pair of int comment. So rather than typing a pair of int comment again and again and again, let's define it as in short as PR. So priority queue of PR. Now, when I make this by default a priority queue is a max heap, but then I need to make a min heap, right? So what I'm going to say is vector of PR and then greater PR. What this is going to do is it's going to convert the default behavior of a priority queue and it's going to behave as a minimum heap. Perfect. Then what I do is basically I start I push inside the priority queue. The first thing that I push inside the priority queue is 0 comma whatever the starting point is, that is k, right? And then I have a while loop. This is standard Dijkstra's algorithm. While the priority queue is not empty, what I need to do is I need to remove the current thing which is at the top of the priority queue. So you can say top is equals to pq dot top, right? And pq dot pop. Perfect. Then for a fact, just like we did in our dry run, so when we were standing at 1, I pushed all of these better pairs. So I pushed 2 comma 10, and then I pushed 5 comma 13. I had 5 comma 13 inside. I had 4 comma 15, and then I had 3 comma 17 at the very last. So we have two things inside of here, right? One thing is the neighbor, which is top dot first actually, and the other thing is the cost, which is top dot second. Now what we do is, inside of our minimum time, we do the comparison. We do the comparison in such a way such that if cost and what's going to be the current cost, by the way. So the cost that I'm talking over here is this cost, but there is going to be a current cost as well. So how do I know what the current cost is? So actually I'm making a mistake over here. What I need to do is the you know this particular cost that I have written is actually the current cost. It's actually the current cost. Okay, then I need to see where I can go from, you know where I can go from uh, the current node. This is not the neighbor, this is the current node. I'm sorry, that's my bad. I need to have a loop over here which does something like this. So for int ngbr, for all the neighbors which you can go from, this is not going to be, by the way, this is not going to be an integer, this is going to be a pair. For every neighbor that you can go from the current node, for every neighbor that you can go from the current node, you have two things: who that neighbor is. So neighbor node, who that is, that's going to be ngbr dot first, and then what the upcoming cost is. So upcoming cost is going to be ngbr dot second, right? Perfect. Okay, and then you are going to actually make the comparison, which is going to be, if current cost plus upcoming cost, if the addition of both of them, if it is less than equals to what is inside minimum time right now, minimum time of current node, or neighbor, actually neighbor node, ngbr node, because we're talking about visiting the neighbor, right? If the current cost plus upcoming cost, if it's less than the minimum time of ngbr of node, which is this 10, this 17, because we can go to all the places from 1, right? If it's less, then what you can do is update. Minimum time of ngbr node is going to be this. Okay, since this is less, and I'm going to push inside the priority queue, pq dot push, what that you can go to ngbr node using what cost, current cost plus upcoming cost. Perfect, just like we did. And that is it. I think that is it. That is our Dijkstra code. Let me, yeah, put that over here. Okay, let's see if it passes the example test cases. It does not push, sorry, priority queue dot push, right? Where is it giving me the error? Line number 19. pq dot push 0 comma k, this needs to be a pair. Okay, perfect. I hope this passes the example test cases. It does not. Why is it giving me, int max in the first test case and then in the second one as well? What is wrong? So I think I have found out what the mistake is. I should have, written it down as, rather than 0 comma k, this is actually going to be 0 comma k, but then the current node is going to be top dot second, and the current cost is going to be top dot first. I think this was the mistake that I'm making, because the node is at the second position and the cost is at the first position. Still, it does not work. Um, this is correct. Neighbor node ngbr dot first, ngbr dot second, uh, top dot second. I'm pushing the value first. Oh, I'll need to make the change over here as well. So I need to push the cost first and then what the neighbor is. All right, I hope this fixes it. We need to pass the cost first because priority queue, sorts by default on what the first value is. I don't know why this is still isn't working. I need to push the cost first and then the neighbor node. Okay, so current is top dot second. All right, sure. Current cost is top dot first. The neighbor node is when you're checking inside the map, and the map is something like this. Why is it still not working? I think I forgot one very important part. Yeah, that's the mistake that I did. I forgot to say that you know, minimum time of k should be 0, and that is why it was actually giving me int max in all of these scenarios, because it was picking up on that. So let's see if it passes all the other test cases as well, right? And it finally does. So yeah, yeah, the dry run was actually very interesting. I hope you found the video helpful, and I will see you inshallah next time. Take care.